Okay, what we're going to show next is that the general polynomial equation of degree bigger than or equal to 5 is not soluble by Ruffini radicals. Okay, so first, a quick proposition. If there exists a tower, as in the previous definition, like this, where you go from one to the next by adding in an nth root, then it can be refined, if necessary, so that nj is actually prime for all j. And the proof of this is simple. We know that kj, as we've said here, is obtained by the previous one by adding in an nth root. So is kj minus 1 alpha j, where alpha j to the nj is in kj minus 1. Well, what we can do is we can write nj as some product of primes. But then we can refine this this tower by setting beta L to be alpha j to the product of the last primes after pk. All right, so then what? Well, beta 0 is just the product of all the primes after 0, and that's just nj itself. So that's alpha j to the nj. That's in kj minus 1. And when we add in the next one, beta 1, that's going to be alpha j to the p2 of the pk. If we raise both sides to the p1 power, p1's a prime, then beta 1 to the p1 is alpha j. Adding in p1 just gives us the product of all the primes, right? Okay, so that's in the previous one, so it's alpha j to the nj. And similarly, beta 2 to the p2 is going to be alpha j to the p3 pk to the p2 power, because that's what beta 2 is. So that's just the product of all the primes except for the first one. That's beta 1. Okay, so what we do then is we refine it. We say kj minus 1 is where we're going to start, and then we add in beta 1, and then we add in beta 2, and so on, all the way up to beta, I think k minus 1. No, beta k. Yeah, beta k. Okay, so you can always refine it so that it's prime. All right, the next item that we're going to prove is a lemma. So assume that we're in the situation where we've refined it so that it's prime. We're going to prove a lemma, and the lemma says the following. It says two things. The symmetric group Sn has a cyclic quotient of prime order p if and only if p is 2 and n is at least 2. In which case, the kernel is an. We saw this already. Okay, this is the image of the determinant mapping from last class was plus or minus 1. That's a cyclic quotient of order 2, and the kernel was an. Okay, so we actually saw this happening, and that's the only possibility, actually. There's no other cyclic quotients. The alternating group an has a cyclic quotient of prime order p if and only if p is 3 and n is 3 and 4. If n is 3, the alternating group A3 is cyclic of order 3. So it is a quotient of itself via the identity map. When n is 4, that's the new thing. Okay, so there's a proof of this in your book. I feel like we've gone pretty far in a lot of detail in this chapter, so I'm going to omit the proof. But I'm just going to remind you, for 1, we had the determinant function from Sn to plus or minus 1 from class, where we represent matrices as permutation matrices, and An was the kernel. So that's showing that when p is 2 and n is bigger than or equal to 2, we have such a thing. That's not the sufficient though. So, or that's not the doesn't show for all p that this is the only guy. So there's more to do here, but I'm going to omit it. And then 2, well, if n is 3, A3 is cyclic. It's cyclic generated by the permutation 1, 2, 3. And so the quotient is just itself. You can quotient to yourself. And when n is 4, there is a normal subgroup, and I always forget how people like to denote this. Let me just look real quick. Yeah. So I'm going to follow the book's notation to call this group V, which is the subgroup generated by the products of transpositions that don't share any numbers. The product of disjoint transpositions. So this subgroup is a normal subgroup of A3 called, or A4, sorry, called the Klein-4 group. And abstractly, it's just Z2 cross Z2. But nevertheless, it's a normal subgroup, and the cardinality of A3 over V is 12 over 4 is 3. Ooh, that's a terrible 3. And so we can quotient out by V to get a group of order 3. All groups of order 3 are cyclic. Okay, so there's our quotient. Wow, I'm just getting worse and worse at writing these V's. Is cyclic of order 3. All right. In the next video, we're going to prove the insolubility by Ruffini radicals for the general quintet.